All right, so after long last, and again, my apologies for all the delays and everything, just as I've been struggling to get back on track with things, try and get this all going again, but finally to some more lecture videos, this time for week 6. We'll actually be doing 3 lecture videos this week. First one, though, right here, is on tornadoes, sort of a continuation of our severe weather and thunderstorm unit from last week. So, starting off with a general typical overview. What is a tornado? Definition: tornado is a rapidly rotating column of air that extends from a thunderstorm cloud to the ground. Typically, you can see this rotating column of air because the low pressure causes condensation of water vapor. So you get this, what we call a condensation funnel that you can actually see. But the tornado itself is actually the full rotating column of air that's in contact with the ground and the thunderstorm cloud. So some things to not be confused with right off the bat. We don't want to confuse a tornado with just a funnel cloud. So a funnel cloud is just when you see a visibly rotating funnel that's descending from a cloud, from a thunderstorm cloud. But funnel cloud does not yet have the actual rotating air, that rapidly rotating column reaching to the ground yet. A dust devil is just a general term for a non-thunderstorm related vortex of air. It could be fairly rapidly spinning and sometimes even could do small bits of damage, but it isn't associated with a thunderstorm, and it's pretty much always much weaker. And so it's just a rotating column of air at the surface. A water spout or a land spout kind of gets a little ambiguous. They can be sort of dust devil-like, where they're on their own and not associated with a thunderstorm, but they can also be a type of tornado if they extend from the ground to a thunderstorm cloud, meeting the tornado definition. Water spout is just the name for it if it's over water, land spout if it's over land. And we'll go into details about the type of tornado that can be associated with these water spouts, land spout type of rotation, rather than the other type of tornado. We'll get to that in a little bit. And then, of course, we're at Iowa State University. We talk about the Iowa State cyclones, and typically we use the image of a tornado to represent a cyclone. Back in the early 20th century, that's typically how they referred to tornadoes in the US, is as cyclones. But now cyclone as a proper term, and really its general term, how it's always been used and now is formally scientifically used, is just counterclockwise in the northern hemisphere rotating air around low pressure, because that's just how the dynamics of the atmosphere work. So a cyclone can refer to a tornado because that's counterclockwise, or sometimes if it's anti-clockwise, counterclockwise rotating. But cyclone can refer to tornado scale. It could be a mesocyclone, the rotating column of air that is the entire updraft of a supercell. Also, we have low pressure systems or mid-latitude cyclones. We also have tropical cyclones that we'll be talking about later. So cyclone is a very general term. Tornado can be a type of cyclone, but tornado is the specific term we use for the weather hazard that is a rapidly rotating column of air extending from thunderstorm cloud to the ground. That's the key definition to keep in mind. So how do we get to a tornado? And this is sort of why I just alluded to there. There's 2 main routes to getting a tornado. There's our sort of traditional tornado, where it's from a supercell, so it's supercellular or mesocyclone. Again, mesocyclone is a rotating updraft of a supercell. And this route, of course, as one of these description implies, we need a supercell first, because it's a tornado that its circulation is supported by the dynamics of a mesocyclone that creates the processes needed. It's a very delicate balance that we don't actually even fully scientifically understand. We have the high level details. We still are narrowing in on some of the specifics about what makes or breaks that process. But that delicate balance of thermodynamics in a supercell is what can get us that rapidly rotating column of air all the way down to the ground surface. And this route gives us the full range of intensities. We'll go to actually how we scale or rate tornadoes later on, but this can go from anything from the very weakest tornadoes to the absolute strongest tornadoes. The land spout route is sort of our other route where instead of using supercell dynamics to get that rapidly rotating column of air at the ground surface, it instead uses existing vertical rotation in the air and just a simple updraft to stretch and intensify. We'll talk a bit more in detail coming up about how that works. But these landspout type tornadoes are non-mesocyclonic. They're still tornadoes. They can still do damage, but they're typically weaker than the ones that we get through that traditional or mesocyclonic or supercell route of tornado formation. So this is the little bit more scientific section of this lecture video. We're talking about vorticity. Now, vorticity is just a term we give for the spin or the rotation in air. If you've ever seen like smoke billowing up from a candle, you eventually get those kind of turbulent eddies, those little circulations. Those have vorticity. That's the little curl or the spin that's in the air. And how we get vorticity in the air is really, it's a change of any component of the wind. So wind in space is three-dimensional, so there's three components. And if that magnitude of the wind in any of those components changes over any perpendicular component, so if the vertical wind changes in either the x or the y direction, or if the x direction wind changes in either the vertical or the other horizontal direction, what that means is that you get a change in wind speed across a certain direction. So if you take the classic trick of like a pencil here, and you get a change in wind across a perpendicular directions, you're going to create spin in between. And that is vorticity. And so since it's the change in any component of the wind, there can be vorticity in all three dimensions or combinations at different angles. So vorticity itself is another 3D vector quantity. So when we're talking about tornadoes, though, and supercells, we're most interested in, at the end of the process, what that actually is. It's vertical vorticity. Our mesocyclones that make up a supercell's updraft are vertically rotating vertical vorticity in a mesoscale sense. Tornado is a very much smaller vortex, and that's sort of on the microscale process where we're just having these vertical vorticity, these vertically rotating columns of air. And when we talk about vorticity from a physics point of view, there's sort of three key physical processes involved. There's generation, which is sort of what I applied before about shear changing directions of wind. But there's also dynamical processes based on density and pressure gradients being in contrast that can also generate that rotation as well. Tilting, where if you have vorticity spinning and then you have wind, you can basically tilt and change the direction that the vorticity is in. That's something that happens, and that's a very important process because in the atmosphere we tend to get horizontal vorticity a lot. But in order to be active, useful vorticity for tornadoes and mesocyclones, it has to somehow be tilted into the vertical. But that final process I have listed there is really the key one for tornadoes because the vorticity that just naturally exists in the atmosphere is not intense enough for a tornado. A tornado is really rapidly rotating, and the vorticity that just naturally develops by either just generation of vorticity or tilting of horizontal vorticity into the vertical, it just isn't strong enough. But there's this little thing called conservation of angular momentum. If you look at the animation that's been sort of playing above my head this whole time on this slide, it's the idea of a figure skater pulling in their arms so that instead of their mass being distributed over a wider area, you narrow it in, and bringing that closer means that you spin faster. Your rate of rotation increases. So stretching of vorticity is the idea when you apply that concept to a fluid, where because of the continuity of the fluid, you can't just shove it all into one space. But what you can do is by bringing it together, you end up stretching it out in the vertical. Or if you have something that forces it to stretch, you bring it in together. It's really the same process when you're working with a fluid. So that's really the key process for how we get from just vorticity naturally existing to the process to actually get it intense enough to be considered a tornado. So this is sort of two illustrations of those routes to a tornado formation I talked about previously. This is the mesocyclone general process where we have horizontal vorticity. We get updraft that both tilts and starts to stretch that horizontal vorticity into a little bit more intense vertical vorticity. But we need a downdraft as well to provide that really sharp stretching to actually get vertical vorticity at the surface in an intense fashion. The landspout route, where we just naturally, because of shear boundaries and land contrast, we already have vertical vorticity existing in the atmosphere. It's just not intense enough to do anything with. And then we get updrafts, and those updrafts, if there's enough stretching, you can actually get a tornado. We talk about dust devils. Dust devils have a similar formation process, just instead of a storm scale, updraft that's causing this. Those are just little heat bubbles on the ground surface that end up creating enough lift from the very lowest levels of the atmosphere to get rapid spin-ups near the surface. So that's sort of the high-level overview of vorticity. We want to get into all the details and why tornado formation is such an interesting scientific problem. It gets really complicated. This is a super high-resolution numerical simulation of a tornado vortex done by Lee Orff's group at University of Wisconsin. They do a lot of fascinating research in this area, and a lot of people are trying to study to understand the details of tornado formation. But it gets really complicated, and we don't really have the full process figured out yet. It's still an open scientific problem where there's a lot of research going into, and I think a lot of really fascinating research. But if we want to actually bring it back to the realm of practicality and not just all the details we want to figure out in research, we can talk a bit about some more useful takeaways about the occurrence of tornadoes and what their impacts are and how to stay safe from them. So this map here is an illustration of where tornadoes tend to form. I'm just showing the US. The US is by far where most tornadoes occur across the world. And within the US, there's sort of two main hotspots for tornado formation that are typically referred to. We have the traditional tornado alley, which is actually, if you go back a few decades, where were some of the strongest patterns. But especially if you start including recent decades, where we actually have a little bit more careful records and can understand the patterns of occurrence, we sort of have this secondary or additional area called the Dixie Alley, where we have a very high frequency of tornado occurrence. And you can almost consider this just to be one central hotspot. But the idea is that these are where the ingredients for intense supercells across the US tend to form with the right shear in order to be conducive for the vorticity generation and downdrafts then needed for forming a tornado. If we look on sort of the small picture, that was sort of where storms that produce tornadoes can end up being. If we want to actually know where in the storm the tornado lives, so sort of a small picture where, we go back to the supercell diagram I talked about before. You've seen both of these before in the lecture videos, is that we tend to get the tornado right underneath the mesocyclone, or right underneath the main rotating updraft of a supercell. And because of the intense dynamics that are going on here, we actually tend to get a lowering, or what we call wall cloud, where we start getting condensation in this updraft area below the rest of the rain freebase area of the supercell. And this is where, underneath that wall cloud, is where there's enough rotation and the combination of the updraft and downdraft interactions are intense enough to form that rapidly rotating column of air that is a tornado. And so you most often in this classic supercell picture will see a wall cloud right underneath the updraft, right by where the main downdraft area is. And then a tornado would form off of that wall cloud. The thing is that we a lot of times do get these wall clouds and then no tornado even forms. So just because you're going to have a wall cloud doesn't mean you will get a tornado. But a lot of times when we see tornadoes, they end up coming from these rotating wall cloud lower rings beneath the mesocyclone or beneath the updraft. We also talk about when tornadoes form. So again, I'll go a big picture and a small picture kind of thing here. So when tornadoes form, they can occur at any time of the year, but most frequently mid-April to mid-June is your sort of climatological period where you get your highest rates of occurrence. And the hotspot, or where the most tornado activity tends to be, actually moves north. So earlier parts of the season, your peak is going to be farther to the south, and then we increase. So if you want to talk about when Iowa is most likely to get tornadoes, that's actually more towards the June period rather than earlier in the season. So if we look at instead when tornadoes form on the small picture or in the context of a given storm, it is during the mature stage of the supercell life cycle. So it's once the supercell has really had a chance to form a robust mesocyclone. So you're getting enough vorticity. It also has a chance to get that both forward flank downdraft and rear flank downdraft so that those interactions end up creating the stretching we need in order to form a tornado near the ground. And that's sort of what you're seeing in this time-lapse video that's playing over there. But it's also usually not going to happen when the storm's dying out, when it's outflow dominant, where you cut off the updraft. Because, again, a tornado forms when you have this delicate balance between updraft and downdraft and vertical vorticity and thermodynamics. And a particular supercell can form a tornado just once, or it can also form it in sort of a cyclical process and form multiple tornadoes over its lifespan. And the other thing is that there aren't, as of our current scientific understanding, there aren't any real indicators of when a tornado is going to form, other than a slight hint that if we have intensifying low-level circulation, so the sort of radar signatures we might be able to pick up from like that wall cloud or a low-level mesocyclone, we don't really have any other indicators of when a tornado is going to kick off. So on radar, that's when you hear about radar indicated rotation indicating a tornado warning, or that's what makes them press the button to end up issuing a warning, is when you see this kind of signature on radar where you have this tight couplet of outgoing and ingoing winds indicating strong rotation at the low levels of the storm. There aren't any other real correlative factors that we know that play into it. At this point, research is ongoing, but things we know that don't or just myths about it, lightning activity. Lightning activity hasn't shown to be any real correlation with the actual formation process of a tornado. Hail, we know that, yes, you can get very large hail on the same kind of storms that would produce a strong enough mesocyclone, a strong enough updraft to also produce a tornado. But we don't have any correlation or understanding yet that the intensity of hail pattern giving a clue about when a tornado may or may not form either. So going into damage, little clip from Twister here, classic movie that, Disney always has the best science, but it's still entertaining and shows a little bit of a picture of what a storm is like. But the big thing about tornadoes is that you have extremely strong winds near the surface, often with circulating debris, on a really tight region. So You can easily go tens of feet over and go from catastrophic damage and buildings being blown to pieces to right next to it just having little minor damage, and then over a little bit more, nothing. And when we rate tornado intensity, even though you may think the most direct thing of how intense a tornado is its wind speed, that's not how we actually rate or scale tornadoes, because we can't reliably measure the winds in a tornado, because we either need a mobile Doppler radar that we can position outside and scan right into the tornado, or we have to have wind instruments inside of it. And the wind instruments tend to fall apart because of how damaging a tornado is, and we can't reliably measure every tornado with a mobile radar. So for consistency purposes, we rate tornadoes, their intensity, by their damage. The scale that's used for that is called the Enhanced Fujita scale. It's a 0 to 5 scale. The percentage here is about how often they occur. So most often we get EF0 through EF2. And if you want to see what the damage of this could look like, this is a situation where I believe this was an EF3 or an EF4 tornado. So you can see the contrast where there's really devastating damage in some areas. Basically, buildings completely demolished. And then over here, somewhere it's just maybe a roof missing. And over here where maybe it's just some shingle damage and roof damage and siding. If you want an actual picture of what this looks like for a well-built home, of course, the Enhanced Fujita scale actually keeps into account building and construction quality. You can see the progression from EF0 to EF5, where EF0 is just very minor damage, things that are loose coming off, shingles being blown off, to EF5, where it's basically clean wiped off of foundations. So one other comment when it comes to damage that I think is just sort of really interesting and important is suction vortices. So a tornado is not usually, some of your small ones are, but your most damaging tornadoes aren't just one simple rotating column of air. It's actually a rotating column of air with smaller, intense subvortices, or even stronger rotating columns of air inside of it, as illustrated by this picture here. And why this particularly comes up with the worst damage is because you have one velocity, so you have the direction that the tornado is moving, so that's one speed. Then you have the velocity of rotation of the main tornado circulation. So you have two, that's V plus T here. Plus you also have the speed at which these subvortices are rotating. And so you add together all of those speeds and you can create really, really strong winds. And you can create patterns that look like this. So you can see the main tornado path follows this damage swath. But within this, you see these little swirls where there's extra damage in this crop, in this particular field. And that's where your suction vortices are creating particularly strong damage in the swirling pattern within the main tornado path. And so once it comes to safety, definitely don't do what they did up there in Twister and just head to a shed and try strapping yourself down. That won't help. The big thing is that debris will really hurt you in a tornado. So you have to think about where can you go to get out of the way of any flying debris. So best place to go, an interior room, reinforced shelter is absolutely best. In a basement, wonderful. On the lowest floor though, that's the key. Best you can to get to an interior room on the lowest floor. And reinforced shelters, purpose-built, are great for this. Of course, not everyone can have those, but if you can, that's absolutely best. You want to avoid windows. Again, debris flying around. Evacuate manufactured homes. Need to go to a dedicated shelter because manufactured homes tend to completely fall apart even in moderate tornadoes. So they're very dangerous to be in, and that's where a lot of deaths occur. So evacuate manufactured homes for dedicated shelters. If you're in a vehicle, key things, drive away from the tornado if possible at a right angle to the tornado path. Because the big thing with the tornado is if you can see a tornado and it's not going left or right, that means it's coming at you. So go to right angles from where the tornado is moving. The other key thing is do not stop under overpasses. Those tend to create wind tunnels that intensify the wind speed even more than the already crazy wind speeds that a tornado can produce to cause a lot of extra damage. And those are also really dangerous places to be in a tornado. So don't stop under overpasses. Finally, if you're in the open outdoors, it's not a good situation to be in a tornado. But if worse comes to worse and you're stuck in that position, get as low to ground as you can. Again, avoid your exposure to flying debris. Cover your head with hands. Protect your most vulnerable areas from debris. And stay in somewhere that's sheltered from trees and weak buildings, places. Again, the key is avoiding things flying in the air that could hurt you. So wrapping up, this was a longer video. Again, I'm really interested in tornadoes as a research and scientific topic. So sorry if I went into a little bit of extra details there. But again, it's important stuff to know, I think. And so wrapping up on an overall sense, this is where I'll put some of the commentary for this week. Sorry again for the delays. Things have been rough for me personally, still trying to get back on track, but I appreciate you working with me, and hopefully I can adjust the timeline on assignments that it isn't putting any extra burden on all of you. And if it is, please do not hesitate to reach out to me. I am totally willing to adjust things, because the important thing about this class is that you learn stuff, that you can take away good safety messages. It's not that you're passing assessments or taking a certain number of quizzes or anything like that. That's not what's important. It's learning this stuff and getting an understanding of severe weather. And so with that in mind, one thing I end up doing is the quiz that was supposed to be on this week's material due on Saturday the 14th has been pushed back because of how late these lecture videos were to next Saturday the 21st. This is, though, during or at the very end of Dead Week prep week. So I don't want to double up on quizzes unless you really want a graded quiz on next week's, the final week's content, which is winter weather hazards. So go on Canvas, fill out the survey by Monday. So I can decide whether to actually make a quiz. The current results are going no quiz. So if that continues, it'll just be, I'll post lecture content on winter weather hazards for your own learning's sake, and to incorporate into the short discussion post if you wish to do so. So with that wraps up our video on tornadoes. Next up is going to be one video on flooding. So I'll see you then here shortly.